Yeah, we can. So how about if we have a look here at oh, you mean on actually 6.1? Okay, yeah, we can. Sure. Okay, yeah, let's have a look at this one. There's a lot going on in this problem. I know you have to do these. I remember having to do these, but honestly, aren't these kind of fun to answer questions like this?
On this one, I've got no idea how to factor in how far below he goes.
Okay. But the process, I mean, you gotta kind of sometimes just embrace your inner geek a little bit. Just let yourself be interested in finding answers to real questions.
I am interested, but I don't know enough to know it.
No, you do. You do. So let's talk about this one. Okay, so let's first of all, let's just read through this together, and then and this is important to do in physics and in calculus, and when you get into highly analytical classes like this, it's really important not to just jump in with both feet. Bad pun, but you get that. You can't just start working the problem before you've had a chance to digest it a little bit. You got to really look at it and think about it, and come up with some kind of a preliminary strategy, some thoughts. Otherwise, you're just too apt to do something wrong and do it for a long time. Like start something wrong and then do a lot of work on it, and then later realize, oh, why did I do that? So you can really save yourself a lot of time by not just trying to be too hasty about it, right? Okay, so we got a 79 kilogram swimmer. So we got the mass of the swimmer, jumps off of an 8.1 meter tower. Wow, that'd be kind of scary. Into a deep pool. The swimmer comes to rest 2.3 meters below the water's surface. The magnitude of the net force exerted on the swimmer by the water is what? Okay, so this is kind of tricky, isn't it? Can you look at the Chromebooks? You can go grab one from Mr. Morioka. Can just bring it down your phone. Yeah. So there's a lot going on here, but really let's just talk about how many parts would you say there are to this problem? Let's just say that. I'm seeing a lot of people saying 2. Anybody says 3? Okay.
3.
You say 3?
Yeah. I just say
what are the 3?
Thinking about it.
Okay.
Doing it and getting it.
Okay. There you go. Okay. The actual problem itself, we could say probably this situation can be broken into probably 2 parts. There's the jump into the water, and then there's the deceleration when you hit the water, right?
If he's jumping out, that makes it a lot more complicated.
Okay, so let's say steps off.
Okay.
Steps off a platform. Okay. So the part that we're interested in probably is part 2, right? Because the question that's being asked is specific to part 2. So we want to know what's the net force exerted on the swimmer by the water. Well, what's going to be the basic relationship? What relationship involves force? What equation involves force? Okay, there we go. Okay, so this is a Newton's second law thing, isn't it? Right. So we've got net force equals mass times acceleration, right? And if we want to know the net force, then what we're going to have to somehow find is the acceleration. We already know the mass, right? So this sort of just becomes kind of a kinematics problem in a way, doesn't it? It's related to Newton's second law by the fact that we're calculating the force, but really most of the work involved here is from previous chapters. We could have had this problem. I could have asked a different question. I could have asked for acceleration, the diver's acceleration when he's in the water, and that would have been something that would have been really just about fair game a while ago, right? So let's think about this then. We got to break this into 2 parts. Part 1 is the dive, right? So what do we know about part 1? What are our initial conditions for part 1?
Acceleration.
Okay, so we could say then it's all vertical, right? So for our variable, let's just use y. That's our vertical variable, right? So we know that y naught equals what? 8.1. Okay, good. What else do we know?
Acceleration of gravity.
Acceleration of gravity, we know. The acceleration is what? Say it again. Negative 9.8. Standard units, right? We're just going standard units here. What else do we know?
Oh, is mass.
Initial velocity is 0. Good. So we know initial velocity. Let's put everything should be awake. Phones, like if you got earbuds in or something, get rid of those, please too. Initial velocity is 0. What else? One other thing we know that's kind of important.
How much weight?
Okay, we do know that, but that's in terms of the kinematics,
where
it's
he
actually not
ends
going to be an
up.
issue. Where's he end up? At
Well,
0.
Well, no,
So,
it
yeah.
goes further down, but in this part.
But for part 1,
Part one is 0.
it's 0. And why? Once again, why do we break it into parts?
So that-
What acceleration change?
Acceleration.
Good. Anytime the acceleration changes, we need a new part to our story, right? So during the first part, the acceleration is just negative 9.8. During part 2, the acceleration is definitely different, right? For one thing, it's going to be positive because it's the invisible hand's pushing upward on the person to slow them down, right? And that's what we're trying to find, okay? But that's what we know from part 1. Agreed? And what is it? Go ahead.
So what is y?
So y is just the height. Like, we would have called it d. Normally we'd call it d, d naught and d. But, sometimes I want to get you used to the idea that if this is just vertical motion only, because we're going to be moving on to two-dimensional problems pretty soon.
Axis.
You see what I'm saying? Okay, so it fits the y-axis,
Okay.
right? Yes, sir.
So, like, your answer in net force is going to need to be positive, right?
Yes, it would be, wouldn't it? And because we know that when the person hits the water, the invisible force is going to be pushing them upwards to slow them down. So we would expect it to be positive. No. Initially, the invisible hand is pushing downwards on them because it's gravity, right? They're being accelerated downwards. Okay. All right. So that's what we're looking for. That's what we're given from part 1. Now let's go ahead and set up part 2 also, because we might need to link part 1 to part 2. Probably we will. So for part 2, that's a P. Part 2, what would we know?
His acceleration.
Well, we know.
0.
Okay, we don't know. That's what we're looking for is acceleration.
Yeah,
Does y equal negative 2?
When y equals 0.
Okay, so the initial position is y equals 0, right? So over here, y naught equals 0. We know something else.
Y equals negative 2.3.
Okay, so the final value of y is what now?
Negative 2.
Negative 2.3, because it's below the surface, right?
Yeah.
And we know one other thing too. Final velocity is what? 0. Aha. I guess I should put vectors on all those when we get to it. Okay, what are we missing there that might be useful? If we're trying to find acceleration, what do you think we're missing there that might be useful? Starting velocity. Aha. If we could add another piece of information there, that would allow us to solve part 2. Well, obviously there must be a link from part 1 to part 2, right? Because wouldn't you agree this problem would probably change if I made the platform higher or lower? Right? That's going to have some impact on how deep the person dives, right? Agreed? So what's the thing from part 1 that's going to carry over to part 2? Yeah, the velocity, right? The final velocity from part 1 becomes what? Initial velocity for part 2, right? So we need to find this. And whatever it is, that answer is going to go there. Right? Everybody agree? Okay, so what's the equation then that would relate all of that stuff? How are we going to do that?
Isn't that the, acceleration times time?
Okay, yeah, what are we missing over there? One that doesn't use time, right? Because we don't have a time. Now, we could find a time, but we're not given a time directly. And so let's see, does that one fit? If we look at we try that one on for size. We're looking at the one where it's v squared minus V naught squared equals 2A delta D, but in our case, it would just be maybe delta Y, the reason why is it's vertical. They could have been D's, would have been fine, just make those D's. And we're trying to solve for V final, right? And so, one thing we could do, anything zero in this equation? Yeah, V naught is already zero. So this is conveniently already solved for us, isn't it? We're already isolating the thing that we need, just if we square root, right? So then V just equals the square root of 2A delta Y, right? Now, also, we gotta remember that this is the equation that only gives us back magnitudes, doesn't it? Right? So the answer we're gonna get out of this is gonna be positive, right? But we could interpret by the direction by the actual problem itself, that what does the sign of V really need to be? Negative. When the person hits the water, their velocity is downward, right? So if we plug all this in, what do we get? So we get square root of 2 times negative 9.8, right, that's A, times what's delta Y?
8.1, or just negative.
Okay, so then that's gonna be positive or negative?
Negative.
Negative, right, because we're
Down.
delta Y is always gonna be the final value minus the initial value, right? That's what a change in means. How much did it change from the beginning to the end? So that's Y minus Y naught. And that gives us back negative 8.1. So everything worked out fine, but then the other thing that I omitted and I shouldn't have, if I square root both sides of an equation, what do I have to include? Plus or minus. Yeah, there you go. And we, of course, in this case, are gonna want the minus one, right?
Yep.
Okay. Okay, so then that's just gonna give us a value of V is roughly equal to whatever that gives us. So the square root, so it's negative, the square root of, what's that number inside? 2 times 9.8 times 8.1. Somebody.
150.
Well, let's go ahead and actually put in an exact. 158.76, and that's exact, right? So that's our final velocity from part 1, right? That becomes our initial velocity for part 2. And I'm just gonna leave it like that because that's an exact answer, isn't it? Right? Or I could just leave it as a decimal in my calculator, either way.
Would it be positive? Inside the root? Be positive?
Oh, yeah, positive inside the root, you're right. Yep, sorry.
Or else it's gonna get real funky.
Yeah, it is. You're right.
Imaginary.
Okay, so now let's take this other part over here. Oops.
Wow.
That way when you're going that way, you're going that way at the same time.
So what's the equation here that we're gonna want? Once again, do you see a time anywhere? You don't, right? So we're gonna have the same equation here that we used there, right? So that's gonna be the V squared minus V naught squared equals 2 delta Y, right? And were any of those zero?
V
Right,
and
okay.
negative V naught is gonna be positive.
And, well, that's a negative V naught squared.
Yeah, isn't it just
Right.
positive though?
So it's gonna be
Okay, but I'm squaring it first and then multiplying by -1, right?
So it's gonna be positive.
So it would be.
No, so it'd be, because, I'm gonna need more room for this. Let me take this,
Just really,
Yeah.
Wouldn't we just be able to take, the mass and our acceleration, everything from part 1, and find out what the net force would be, and then that would be negative, and then just take whatever positive, and just take the.
no, it's gonna be different though, because,
It would end up being
and I think everybody would agree, you're gonna feel more pressure on your body when you hit the water, right?
It's like when
See what I'm saying? So there's gonna be a larger force decelerating you than there was accelerating you.
Oh,
Okay.
That'd be crazy if when you like jumped off in the cliff, so you just felt like instead of just like feeling force
I know
of
what you
the
mean.
water, instead of when you hit the water, that's on you when you first jump.
I see what you're saying.
So you jump and then you're like,
What, like, as you
I don't know
jump,
what you're
that,
saying.
I see what, so, you know, it hurts, there's a lot of force when you hit water. What if that force, instead of when you hit the water, happened when you first jumped?
yeah.
So it feels like opposite.
Yeah.
But you wouldn't have enough space.
Okay, so would everybody agree, if we're gonna solve for A, all we're gonna do is just divide both sides by 2 delta y, right? So we end up then with A equals what was on that side divided by 2 delta y. So let's plug and check. So we get minus, now look what this is gonna be here. This is gonna be that thing, right? So it's gonna be minus the quantity negative square root of 158.76 squared. So Lincoln, what's the sign gonna be of the top then? That's just the top, right?
It's gonna be positive.
You sure? Because if I square this negative,
It's gonna be a positive.
it's gonna be positive, but then times that other negative, right?
I
See what I'm
thought,
saying?
I thought it would just get rid of this square root.
No, it's gonna get rid of everything, because I'm gonna square both parts. I'm gonna square the negative 1. Anything squared that's, any real number squared is positive, right? So then this is gonna give me, on the top, what number in fact?
Negative 158.
Negative 158.76, right? Everybody see that? Because the squared is canceling both the negative and the square root, right? So I got minus 158.76 divided by what? Well, on the bottom, we've got 2 times, what's my displacement? What's delta y?
2.3.
Negative 2.3. Good, right? Because I'm y final minus y initial is negative 2.3 minus 0. But just think of it in terms of the problem. Think about the displacement. This is when the diver hits the water, then he's going to travel, or she's going to travel another 2.3 meters down, right? So that's still negative, right? The displacement during part 2 is still downwards in the water. So it's got to be negative. So negative 2.3 times the, what are we looking at? Oh, that's it, right?
So it really didn't matter which, if we took the, if we took negative or positive, it would come out negative anyways.
No, it actually does come out to be the right sign, doesn't it?
Well, yeah,
Because we get-
so it's the same either way, that's what I'm saying.
Yeah, yeah. So negative over negative is positive, and so it really does turn out to be the right sign. And what answer do we get? And we're gonna round this to how many places if we go back to the original problem? How many sig figs, I should say, not places? We can keep 2 sig figs. So if we go to the next page, somebody find out what is that? Divide 158.76 by 4.6. 35? Okay. So that's pretty big deceleration, right? I mean, that's, well, it's
Yeah.
pushing,
So it's like,
that's about, it's about 3.5 Gs, so it's a lot, yeah.
So when we like
Wait, yeah.
jump
Wait,
from a
why do we
high
round
point
it
and
if
get
we
out
want our
into
answer?
water, then
Why do we round that if that's not our
we're
answer?
feeling G's on.
Yeah, anytime you jump and then
No, just the answer is, Newton's. The answer is.
you jump off the
acceleration.
All right, what was the question again, sorry?
Why do we round that? If that's not our final answer.
It's not your final answer, you're right. So I was thinking that was, it's not, so we wouldn't.
oh,
So we keep this unrounded answer, because we're trying to find force, aren't we?
yeah, and that was just,
So how are we gonna find force?
then you gotta multiply that by 2.
By the mass, absolutely. So we're gonna take this answer. And I guess we're making the assumption, but you gotta kind of make these assumptions when you do physics problems, that when you're in the water, you're just buoyant, right? I mean, you're just gonna be just neutral buoyancy where you just are kind of floating there, you're not sinking, you're not rising, essentially, right? If you are, it's really, really small accelerations either way, right? So then the force we're experiencing is just gonna be ma, and that's what we're plugging in for A, unrounded, right? So somebody who's still got that in your calculator, multiply that by the unrounded acceleration What's our mass? 79. Multiply by 79.
2,726.53.
Okay, so then that's gonna be roughly 2,700.
Well,
Roughly 2,700 meters. Uh-uh. No, because because now you're just in the water, right? So when you enter the water, it's a totally different story.
Oh, by the water.
Yeah, by the water. Yeah. Okay. Makes sense. So that's about, ballpark. That's pretty big force. Ballpark. That's going to be about 650 pounds of force.
So how tall?
No, it's spread out over a large area.
How tall is 8.1 meters?
That's
Times 3.
25 feet-ish. That's pretty high. And I don't know how reasonable it is that you're gonna stop. I guess if you cannonball, that's probably about right. You wouldn't go very far into the water. It also hurt.
How much?
Yeah, belly flop, you
How
really
much
wouldn't
does-
grab.
Yeah.
How much does this person roughly weigh in pounds? 79 kilograms.
79 kilograms, so
Or
that's
about
gonna be
175 pounds. I would put that.
80 digits, so it'd be 160. Yeah, wouldn't it be a little more than that, 2.2, so
It's
it'd
like
be,
175 point something.
okay.
So then, if you took and you added more weight to this equation, they'd be experiencing more.
Yep. More mass, yep. Mhm.
That makes sense.
Okay, so that's no problem. All right, let's look at some of the newer stuff. How about something like this? 6.2 part 1. Let's just talk about a few of these. So this one looks like it's got, I don't know how many problems, 6 problems, but it should go really fast. These are all essentially the same. If you had to label what this one is about, you would say this is about like apparent weight, maybe, right? So a person stands on a scale in a stationary elevator, and when he does that, the scale reads 679 newtons, okay? What would the scale read when the elevator is moving downward at a constant speed of 2.2 meters per second?
There's constant speed wouldn't be the same.
Everybody see that?
Could you just divide 679 divided by 2.2? No, there's no acceleration.
No, you don't have to do because there's no acceleration. When you're standing, think about this one. If you're standing at rest in the elevator, right, what are the forces acting on you? Your weight is pushing down, so the force of gravity. What's pushing up? The normal force, which is what the scale is actually measuring, right? So the scale is measuring your weight because there is no acceleration going on, right? The net acceleration is 0, correct? Okay, so those two forces would have to cancel. Does everybody see that? Right? Okay, what if the elevator is moving at constant speed? Well, if it's constant speed, is there any acceleration?
No.
No, it's gonna be the same thing. Okay, now let's change it up a little bit though. Let's change it up and so that one's pretty easy, but this one's a little harder. Okay, what if this time you're standing in a stationary elevator, this person, the scale reads 661 when they're at rest in the stationary elevator, okay? The elevator begins moving downward with an increasing speed. The speed is increasing at a rate of 2 meters per second squared downward. Now imagine what that's gonna feel like to you. If it's at rest and all of a sudden it starts to accelerate down. What are you gonna notice? Okay, you're gonna feel lighter, you're gonna feel less pressure with your feet. So you would describe that probably as, I feel lighter, right? What would the scale read? It's gonna be less, because the scale is measuring that force that you're feeling as pressure in your feet, right? So it makes sense that the scale should have a smaller reading then, shouldn't it? Right? If we were to draw a free body diagram for this one, okay, so if we were going to draw a free body diagram on this one, it'd look pretty simple, right? It would just look like, here's our object, which is you, right? The downward force is what? How big?
The downward force is 6.61 times
Well, it's gonna be 661, right? Because that's your weight, isn't it?
That's the,
Right, when you were at rest, the
Oh.
scale was pushing up as hard as gravity was pushing down. And so that's the magnitude of the gravitational force, right? So that one's pushing down. Now, what about if it's moving downward with increasing speed? What do we know that, if I were to write this in terms of a net force vector, what's the net force vector gonna have? Where's it gonna have to point? Down, because you're being accelerated downward now, right? So the net force would have to look like this. Okay, this is mg, that's your weight. The upward force is the normal force, right? And so you know that the combination of those two added up has to be negative, doesn't it?
Yeah.
Right? Okay, so then we can come up with a pretty simple equation here. If we know that the net force is just the sum of the forces acting on the object, there's only two of them, right? So our equation's gonna be normal force minus mg, because it's going down, right? We're just adding them up. That one's negative, isn't it, right? Is equal to our net force, which is what by Newton's law?
or net
Oh,
force?
mass
Mass
times
times
acceleration.
Mass times acceleration, right? So in other words, and we're looking for, what are we looking for? Oh, we were given acceleration, we're looking for the normal force, aren't we? Right? Okay, what do we not have to add into, to dump into those equations though? We know G, we know A, it's given to us. We don't have the mass. How could we find the mass?
Well, does it give you the net force? 661.
Okay, I'm hearing lots of stuff, I can't tell.
acceleration, we have it. Is net force 661? So.
That's important.
1 divided by acceleration.
Divided by what?
Acceleration.
9.8.
Ah, okay. Look at the part in purple here. This is kind of the first situation. When the elevator's at rest, you already told me earlier that the normal force and the weight have to cancel, don't they? Right? In other words, normal force minus mg equals 0, or normal force equals mg, right? Well, they're telling us the normal force when the elevator's at rest, that's what the scale is reading, is 661, right? So then we get the equation 661 newtons equals m times g. Well, g is just 9.8, right? So how do I find the mass? Yeah, divide by 9.8, which you'll come to do just almost automatically, right? We know that if we're converting a weight on Earth, if we're converting a weight into a mass, well, we just gonna divide by 9.8, right? Okay. And so if we do that, we're gonna get our mass. So our mass, that's our mass. So if that's our mass, and we're trying to solve for normal force, now all we gotta do is just move the mg to the other side, right? And find out what we get. So normal force would equal ma plus mg, which is that number, right? Times a plus that number times g. Could I even rewrite this in a simpler way? I don't have to, but is there a way I could rewrite this that might even make more sense? Well, I mean, what could I do with the m's there on the right side? Okay, I could, and you don't have to do this, but if you're comfortable with the math, doesn't it make sense there maybe even to factor out an m? Because then look what you're getting. You're getting normal force equals mass times the sum of the acceleration plus gravity, right? Now, what's the acceleration if we're moving at 2 meters? They tell us this. moving downward, increasing our speed at 2 meters per
So
second
if
squared.
gravity was positive, then it's positive.
Okay, but G, the number G is 9.8, right? We always put a negative by it though to mean that it's, right? But we already got rid of that. We already dealt with that, right? We know that we subtracted mg because this was pointing down and that was pointing up, right? So this is just, we know that one's 9.8, but what's the acceleration? We haven't accounted for the sign of the acceleration yet. You tell me, based on this picture, or on this description,
So it's negative.
it's negative, right? Because the invisible hand is pushing us down, we're accelerating downward. Agreed? Okay. Our velocity is increasing downward at a rate of 2.00 meters per second squared. So then when we get our final answer here, it's just gonna equal that number times negative 2.00 plus 9.80. Right? What's it give us? We do that, somebody. What's 661 divided by 9.8 times 7.8? Thank you, sir. So what's it give us? Somebody.
526.102.
Okay, so we can keep, I think, was it 3 sig figs?
Yes.
Yeah, 3 sig figs. So it's roughly equal to, what was it again?
526.0 or 0.1. So
526. So that's what the elevator with the scale would read, right? Does that make sense? Okay, prove it. Let's try one of these. How much time we got? 2 minutes.
Is there an easier way to solve that? than having to
Do all that.
Well, not really, but I think because it always seems harder the first time because there was a lot of discussion. I think what we really did, let's just recap, hit the highlights here. What did we do? So we figured out, we got the mass by dividing, listen please, don't, hang on for 1 sec here. Let's just recap this real quick. So we know that when the elevator's at rest and normal force is equal to weight, just opposite directions, right? They offset each other because there's zero net force. Well, that's the normal force, so that must be the magnitude of the weight also, right? So if I want to find the mass, I just divide the weight by g, because mass, weight equals mg, right? So that's going to give me the mass of the object. If I know that it's accelerating downward at 2, so the acceleration's negative 2, then look what we did here. We just took this free body diagram and we said that the sum of normal force, and negative mg has to equal ma from this free body diagram, right? That minus that equals that, right? And then we just plugged in what we know, okay?